Fine, we'll start the wave optics. Yeah, you can see now wave optics. So till now we have discussed about the ray optics. The ray optics will consider the light as in the form of a ray. Light ray will travels in the form of a straight light, which is in the form of a particle in nature. By considering the particle nature of light ray, we have analyzed the concept of reflection and refractions. We studied about the reflection and refractions we have studied. But here we used to consider light as a wave will consider. Here we'll consider light as a wave nature. By considering the wave nature, here we are going to see the phenomena called as a principle of superposition, interference, superposition of waves, interference, and diffractions will study. And there is one more nature of the light that is polarization. And to understand the polarization, we need to treat the light as an electromagnetic wave. Light as electromagnetic wave. By considering light as electromagnetic wave, we'll study about the polarization of light. Right. So here now, so these are the conditions for the when to apply the ray optics, when to apply the wave optics. The conditions to apply this as a ray optics is, so here if b square by lambda into L, if it is very much greater than 1, then we can apply the ray optics. Then we apply the ray optics if it is satisfied. And b square by lambda into L, if it is comparable, it is nearly equal to 1, less than 1, in those cases we'll go for the wave optics, where b is what will be now size of the object. B is the size of the object and L is the distance. Lambda is a wavelength. L is the distance. Lambda is a wavelength of light. Okay. Next. Wavefront. Mm. Yeah, b square by lambda. B is what will be now size of the object. Size of the object. And so, and the lambda is the wavelength. For example, we have taken, this is some object we have taken. Now, the size of this object will call, now this is the size of the object, we can say. Now, L is the, so from light source is coming from here to here. Light is here. And this distance we need to consider as a L. And the lambda is a wavelength of the light. If it is very much greater, that means the size of the object is high, very high, then obviously this value greater na, b square by lambda L is greater. If the b square by lambda L is greater, then what we can use now, we have to use the ray optics in those cases. If the size of the object is high, in that cases we'll go for the ray optics. If the size is small, then we should think about the light is a wave nature in those cases. Right. Next, wavefront. Wavefront means what? The locus means like joining all the points. The locus of all the points of the medium. All the points, locus of all particles of the medium which are vibrating in the same phase, is called wavefront. The locus of all the points we used to call it as a wavefront. We have to talk about different type of wavefronts are there. One is spherical wavefront. Spherical wavefront means, for example, we have taken one point source, we have taken, this is the source. Now, from this source, if we have taken like this now here, if we have taken this point, this point, all these things are equidistant from the source now. So now these points will vibrate with the same phase. Now here this point we have joined. So this point all vibrate with the same phase. Have joined with a line we have joined. If I join all these things, we'll get in the form of what shape will be formed now? Three-dimensional figure will be formed now. Yes, that is called as a spherical wavefront. Three-dimensional figure. The wavefront formed by the point sources is the spherical wavefront. Okay. Now for the spherical wavefront, the condition amplitude is proportional to 1 by r. Amplitude which is proportional to 1 by r. Amplitude. Intensity means intensity is a square of the amplitude. Intensity is a square of the amplitude. That's why intensity proportional to 1 by r square. Intensity proportional to 1 by r square for in case of a spherical wavefront. So these points are at the same distance now. These are called it as a wavefront like this. Fine. Now cylindrical wavefront. Cylindrical wavefront. So if we have this, let us say we have one line source is there here. Now we need to see this thing. We need to take some point which are equidistant. Now here at some distance of here. So then this distance, and we have taken now here this distance same now. Like this will form now here this distance. Now here we should take the same distance. We'll take this side also. And so the top and bottom also will take now. I have taken, this is my light source now. Here we take one point. Here we take one point. Here we take one point. And so along this line will take, along the circle also we can take now. Then what the shape will be formed now like this. If we join all these things, then what type of shape we can able to form. So here we have taken this, we have taken this side, and equidistance we have taken here also. Equidistance from the source. Then we'll form like this. We'll form the shape. It could be formed like this. Will form like a cylindrical shape will be formed like this, isn't it? So then this is called as a cylindrical wavefront. Okay, for cylindrical wavefront, so this is called a cylindrical wavefront. For cylindrical wavefront, so amplitude is proportional to what you tell me now? Amplitude is proportional to 1 by root r. Okay. And intensity proportional to 1 by r. Intensity proportional to 1 by r. Okay. Next one. Plane wavefront. Plane wavefront means if the sources, whatever may be the sources, may be a point sources and line sources, if the sources are very long distance, then we can call it will be form it as a then it will form it as a plane wavefront will be formed. If the distance is very long, very large distance, then will form a plane wavefront. As the light rays are very long distance, and if we observe this light rays are like this, and this if the light rays are very long distance, then it will be appears in the form of a straight line. Straight lines means they will call it as a plane wavefront will call, and we'll call this as a plane wavefronts like this. These are called as a plane wavefronts. Actually, if you want this thing more accurately, plane wavefront, how to visualize, you can see like this. These are the plane wavefront. Okay, like a plane. So here, like we can place one paper like that. So these light rays are moving like this. These are called as a plane wavefronts. In case of plane wavefront, amplitude and the intensity both are independent of distance. Plane wavefront amplitude and the intensity are independent of distance. Next, Huygens wave theory. Huygens wave theory. What the Huygens wave theory means? Simple thing here. Let us consider here this point is the some light source. This is some light source. This light source will form the wavelets. It will form the wavelets are formed like this. Light will move like this in the form of wavelet. Now, so this is called as a wavelet, and this is every point. So here every point in the primary wavefront. So this is every point in the primary wavefront will also generates the waves. Now here this point will generate the waves again. So this point will behave like a source. Then it will generate the waves like this. And this point, each and every point, I have randomly taken some points now. This point is also behave like a source only, and this will generate the waves. And this point is also source only. So here, and this will also will generate the waves. Each and every point. Understood what I'm saying? Now again, this point also will behave like a source, and this will generate the waves. Like this continuously, it will be the waves will travel. Understood what I'm saying here? This is the main source. This is the primary source, actual source, and this every point on the primary wavefront. This is the primary wavefront, the yellow one, will behave as a secondary source. This also will behave like a source and generates wavelets, and which spread out in the medium with the same velocity as that of light in forward direction. Okay, this is the Huygens wave theory. Done. Hmm. Yes, now this point also will generate waves. This point, each and every point also will generate the waves. Okay, this is called as a primary source, and these points are also called it as secondary sources. From that secondary, so that wave will behave like a source of the remaining. Okay, so this point, this is generating this primary wave. This is the primary wavefront. Yes, that will keep on. So every we'll call it as a every point in the secondary wavefront. Every point. This point will generate. This point will generate. This point will generate like this, so on. And those waves will spread into the medium. Okay. So in that manner, the light will propagate here. This light is propagating in this direction. Keep on will happens like this. Hmm. Next, interference. So the interference means the name itself indicate now simply thing is mixing of the two signals, two waves, mixing of the two waves. If the two waves mix together, then as a result, what happens now here? At some locations, we have a maximum may come. Some location, it may have a minimum will come. The two light rays are there. You might be observed here when the two lights in your room is on, at some location you can find some dark spots. You can find at some location you cannot see some location in the room. If you switch on the two lights, at some location we have dark, some location you can find the bright. You can see that is because of the interference. Dark locations we'll call it as a destructive interference. And the dark is formed, that means intensity minimum, that is called as a destructive interference, and the bright is called as a constructive interference. Okay, so that we are going to analyze now here. The simple thing is interference means what? Tell me now. When the more than one wave is there, one light wave, we are talking the light waves. When more than one light ray is there, light wave sources are there, those will mix together. They will generate at some location bright, some location we have a dark. You can see. And when you are driving on the road also here, this is poles lights are there now. At some location you can find the dark. You can find even the light is there. That is because of the destructive interference. So let us consider I have two waves are there. let us say one wave I'm calling V1, which will be equal to A sine omega t. And this is Y2, we have calling it as A sine omega t plus some theta. Theta is the phase difference between the two waves. Okay, these two waves are mixed together and then they will generate the new waves will generate. And the new wave, the resultant wave is given as the resultant wave. So we'll call this as Y, which will be given as this is Y1 plus Y2. Now we'll talk about the resultant wave analysis. We are going to resultant wave also will have some amplitude. Here these are the amplitude of the waves. Phase difference between these two waves is something theta. Now we'll see the resultant of these two waves, that is called as the resultant amplitude. These formulas are important. Resultant amplitude. So this we are calling it as A. If I call, you may say this AR. So that should be given as simply like a parallelogram law, which is equal to A1 square. We have taken this is, let us say this is A1, this is A2, different amplitudes. A1 square plus A2 square plus 2A1 A2 into cos theta. Theta is the phase difference between these two. We have theta na, that is theta. Resultant amplitude, which is given as square root of A1 square plus A2 square plus 2A1 A2 cos theta. Okay. And the resultant intensity. Resultant intensity. Intensity means what will be now square of the amplitude. Intensity proportional to square of the amplitude. So this is IR. If I say square of this thing will come it as what will be now A1 square plus A2 square plus 2A1 A2 into cos theta. Okay. So these two formulas are very important. So this resultant intensity, this we can convert it as I1 square, we can say as intensity of the first wave, and this we write it as intensity of second wave plus 2 into this we can write as, so this is I1 I2 into cos theta, right? These two formulas are very important. These two formulas try to remember. Resultant amplitude and resultant intensity. Here this for cos theta no root, remember. Cos theta no root here. But here cos theta root is there. Okay. Now, so based upon the angle, it will be changes. If the angle is given, so different angles will see the amplitude and intensity will see. Now, so here if theta equal to 0, theta equal to 0 means cos 0 value how much? Yes, so then it will becomes what, tell me now, how much the resultant amplitude will becomes, that is square root of, what tell me now, a1 square plus a2 square plus 2a1 a2 into cos theta. Cos 0 is 1 na? Will come a plus b whole square form. Then how much the intensity will come here? This is a1 plus a2. This is what we can see in a whole square. A1 plus A2 whole square, and this is for root. Then how much is AR value now here, which will come to be A1 plus A2. We are adding this thing. In this case, the intensity is maximum. This is called as A max, maximum amplitude. Next, the whatever the intensity, tell me now here, intensity which is given as, what tell me now, I1 plus I2 plus, what tell me now, 2 into square root of I1 I2 into cos theta. Theta value how much now? 0. Cos 0 value 1. So then it is IR. This we can write as, you see this thing, I can write it as root of I1 plus root I2 whole square. I can write, check it. Now here in this case, this is the intensity maximum. This is called as the I max. So we have the maximum intensity possible if the theta equal to 0 degrees. And the maximum amplitude is this much, and this is the maximum intensity. Now if the theta equal to 0, then we can call this as the constructive interference. This is called as a constructive interference. Okay. Next, if theta equal to, let us say, 180 degrees, cos 180 value how much? -1. So then as a result, the resultant intensity, so here will come, minus will come na here. Then it will come to be, what tell me now, will come A minus B will come. So that means A1 minus A2 will come. Okay, so then in this case, this is called it as, what tell me now, minimum intensity. Yes, then what about the resultant intensity will come? You see this thing here, that is square root of I1 minus square root of I2 whole square. Earlier plus, it is a minus na. This is called as, what tell me now, intensity minimum. Previously maximum, now it is minimum. Okay. And this is called as a destructive interference. This is called as a destructive interference. Fine. Hmm. Now, here you need to understand some important highlighted points. Copy now these things. This constructive, destructive interference, these things are very important. Look at now here from this. Some important points I will tell you, so note down these points carefully. Summary for this thing: constructive interference, destructive interference. Okay, see these points now here. These things very, very important. So based upon this, you will get the problems will come. So first thing here, constructive interference conditions. To have the constructive interference, remember here, the condition for the path difference. Path difference. Path difference will call. How much this path difference is a delta x path difference, which will be equal to n lambda. Path difference is how much? N lambda. For the constructive interference, path difference is n lambda. Okay. Next, so where n is any value, n value 0, 1, 2, 3 like this. So it may be 0, maybe lambda, 2 lambda, 3 lambda like that. And phase difference, keep in mind, this is another important thing here. Phase difference. Phase difference is delta phi, we should call, which is equal to 2n pi. That means even multiples of pi. Phase difference is 2n pi, even multiples of pi. Right. Next, when you are coming to here, destructive interference. For the destructive interference, path difference. Path difference. Delta x path difference is how much this value? Here n lambda, but here it is a 2n minus 1 into lambda by 2. Odd multiples of lambda by 2. 2n minus 1 into lambda by 2. N value start from 1 onwards. Next, phase difference. Phase difference, that is delta phi. How much? This is also 2n minus 1 into pi. Odd multiples of pi. Here it is even multiples of pi. Here it is odd multiples of pi. Right. So that means how much the path difference we need to have? Tell me now to have a destructive interference. Lambda. 3 lambda by 2. 3 lambda by 2. 5 lambda by 2. 7 lambda by 2. Like that we need to have. And phase difference is pi. 3 pi. 5 pi. 7 pi. 9 pi. Like that. For the constructive case, path difference is 0. Lambda. 2 lambda, 3 lambda, 4 lambda like that. And phase difference is 0, 2 pi, 4 pi, 6 pi like that. Here the even multiples means constructive, odd multiples means destructive. Right. Next. Here. So this is a max. Maximum amplitude will come here in the constructive. How much this value? A1 plus A2, maximum amplitude. In case of a destructive, we have a minimum amplitude. How much the amplitude is? A minimum amplitude is A1 minus A2. Next. Here the intensity maximum, that we can say I max, which will be equal to, this is square root of I1 plus square root of I2 whole square. Here the intensity is minimum, that is given as square root of I1 minus square root of I2 whole square. This thing. So these 4 points in the constructive, destructive, you have to remember to solve the problems. If they given constructive, destructive, this one. If not, then in that case, resultant amplitude, resultant intensity. We have seen these formulas we have to use if the angle is other than 0, 180. Okay. Next one. Another important thing is Young's double slit experiment. Young's double slit experiment. What the Young's double slit experiment is? And here we have placed one screen, we have placed here. Here this is the screen. And here we have the source we have. This is the source, light source. And so at some distance, now here, let us say here, at this location we have a small slit is there, S1, S2, that means small holes. For this one we made very, very tiny hole. Right, so then the light ray which is coming, which will come like this here, and this light ray which is come like this. Okay, now if we observe carefully here at the center point, this one at the center, the light ray has to travel from this slit to here, and this slit to here will travel like this. Okay, now you see this thing here. Now from this S1, if I call this point is O, tell me now how much is S1 to P here. S1 to S2, we have the distance is then at this distance, we are calling it as a small d, I am calling, and this distance is calling it as a capital D. Okay. Now look at now here. So what the distance now S1 to O distance and S2 O distance is both are same or different? Yeah, S1 O. So this means S1 to O distance, S2 to O. How these two distances are same or different? Same. So that means what, tell me now here, if these two are equal now, that's why what happens now, delta x is what are the path difference. Path difference means distance difference. Path difference is 0. If the path difference is 0, that means what type of interference will happen? Constructive or destructive? Path difference 0 means what type of interference will happen? Constructive or destructive will happen? Yes, the path difference delta x is 0. That means phase difference is also 0 only, na? So that's why here at the point of what type of interference will happen? Constructive interference. Yes or no? So that means if the constructive interference will happen, so how the intensity is a maximum or minimum? Yeah, so intensity is maximum or minimum? Yeah, see that one. What type of interference? Constructive interference, what we have, maximum intensity or minimum intensity? Maximum intensity. Maximum intensity means that O, that point will appear very bright. Okay. Now, so that means this bright, which is called as central bright. This will call it as what, tell me now? This is O. This is called as central bright. At the center, we have a bright will be formed. This is called a central bright fringe. Central bright fringe at the point O. Now we have taken at some other location we have taken here. Some other location we have taken at the some other locations. So here we have taken randomly have taken the point we have taken here. This point. Then see this thing at the point, at this point, what will happens now here? Can you talk about this one? Minimum or maximum we should talk now here in this case. Now here the distance, the light ray which is going from S1 to P here. And the one more light only here only this hole is there. This remaining part is completely blocked. Okay, very tiny holes. Then the light can able to spread like this only here at this point. Okay, now so we need to see this thing here. In this case, what happens, you tell me now here? S1P distance, S2P, is the distances are same or different? Yeah, S2P is more compared to S1P na? Yeah, so that's why there is some path difference between these two rays. If the path difference is there, then what happens now here? There may be a constructive interference may happen, maybe destructive may happen. If the constructive will happen, we have a bright. If the destructive will happen, then we have a dark we have. So that we need to identify this thing here. For this purpose, what we have seen now here, I'm drawing one perpendicular line from point S to S1 to S2P line. This thing, perpendicular line. We have drawn like this. Now, if we observe carefully, this point, if I call it as this point we have, let us say this point we have taken as something A if I say. Now, S1P and A2P, the distance same I can say. These distances are same. Now, but so S2P, this much is more na? Okay, so that means what we can say now here, S2P minus S1P we have now. So how much this value? This is extra by S2A, this much. Yes or no, tell me. And so we have seen now from here to here, this distance we have taken as small d. Right. Now here, so if we have calling this angle is something theta. Right. So this is 90 degrees. Now you can see that this triangle now here, this triangle which is like this. Now this is S1 and this is S2, this is A, and this angle is theta. Now from the triangle we need to get what this distance we need. S1 to S2. How much this distance you tell me now, D na? Now tell me now from the triangle if we take it as a so here we cos angle, a sine angle will take now here this angle. Okay, 1 second here. Here which angle is given now here we need to see this thing. Not this angle they given. Yeah, this angle they given. Okay, they have given. Generally they will give this angle, they will give this angle. Okay, this angle they will give. And this angle is 90. Okay, now you tell me now from this. If you draw this triangle, now this is S1 and this is S2, this is A, this is theta, this angle is theta, this angle is 90. Now you tell me now S1, S2 distance is D. From the triangle, we can take the sine theta. Tell me now. What is the sine theta now here, which will come to be a what? Tell me now. S2a by d na. From this S2a equal to how much now? Tell me now. S2a, which is equal to how much? Equal to, we'll get the d sine theta. Yes, so that means S2p minus S1p, which is equal to what? Tell me now. D sine theta, isn't it? Where S2p minus S1p, this is called it as what? Tell me now. Path difference. Path difference is how much now? D sine theta. Okay, based upon this path difference, we can able to talk whether we have a at the point P what type of interference will happen, whether constructive happened or destructive happened. This point clear? Right. Hmm. Now here, so at the point P, what can be happens now here? Maxima will happen or minima will happen? What we can have a maximum may happen, a minimum will happen. So we cannot say directly. How we can say now here, if the two waves interfere, if the in the constructively means phase difference is 0. Then if the two waves amplitudes are added, then we have a constructive will happen. If it is the phase difference, the two waves are out of phase. Out of phase means 180-degree phase. If the phase difference is 180, then what happens? We have then there will be destructive interference will happen. The resultant intensity means subtraction. I minima will happen. So that means decided by who will decide now here? This term will decide. Path difference will decide. If the path difference is n lambda, path difference is what? Tell me now. What is the condition for constructive interference? Condition for constructive interference path difference is how much? N lambda. And for destructive interference is 2n minus 1 into lambda by 2. Okay, so this condition. So here we don't know at the point P whether the path randomly we have taken the point P we have taken. Whether this is a constructive interference will happen, so destructive will happen, we don't know. So that's why we have to analyze that one, each and everything. Understood? Yes, so that's why do remember here path difference is how much now? Delta x, which is equal to how much now? D sine theta. Right. Copy this thing. So actually this figure it will appear like this. We visualize. So that means here at the center we have a bright only will be formed. Exactly at the center, bright will be formed. After the bright, we have a dark. This is a dark. This is called as central bright. This is a central bright. And so then next, after the bright, we have a dark will be formed. And so then this is called as a next one immediately. This one, this is called as a first dark. This is called it as a first dark. And then this is also called as a first dark. And top and bottom both will be formed. Next, after that, again we have this is the first bright. First bright. Next, again this is the first bright. Okay. Next, this is the second dark. Next, second bright. Like that will be keep on formed alternately. Bright and dark will be formed. So at the point P, we don't know whether maybe bright may form or dark will form. So that we are going to analyze now. Okay. Done? Yeah. Now here, this distance is there now. So here at the point P, we don't know which bright is formed. First bright is formed, second bright, third we don't know. Our first dark, third dark, we don't know. That's why we have taken we have taken this distance, we have taken as yn. From yn, that is measure from central bright is a reference, from there we'll measure always. Okay. Now at the point P, if it is a bright, let us say, at the point P, if it is occurred as a first bright, yes, let us say at the point P, if it is a nth bright, we consider, let us say, case 1. Case 1, what we have considered now, at the if the point P is a bright, if P be the nth bright, you can write nth order bright. Nth order bright fringe. Then what is the condition for the bright fringe? Yeah, so that means path difference. Yeah, path difference. How much must be delta x? So generalized form we can say n lambda. N value 0 also. 0 lambda like this. Okay. Now here, what is the path? 0, but so here n value 0, that is one possible case. There are so many possible cases are there. Lambda also we have maximum. All these cases will get. That's why only we have so many brights we have na. So at this location we have a 0 phase difference, path difference. In this case we have lambda. Here we have 2 lambda. Next we have 3 lambda. Like this will happen. Okay, so that's where the point P may be any location. Now we don't know. If 0 means that is central bright. Okay, so that's why general solution is n lambda. And we have seen the delta x path difference we have seen in this case, that is S2P minus S1P we have seen, which is how much now? D sine theta in this case, and D sine theta. If you see what is the sine theta from the triangle, we need to see here. Look at now sine theta from the triangle here, this triangle. So here from this a big triangle you can see now. From here, this thing. Yes, so here this triangle. So this is how much now? This distance is D, and this is what you tell me now here phi n. From the triangle, can you tell me tan theta? So how much the tan theta now from the triangle? How much the value of tan theta now? Tell me now here, which will be equal to yn by capital D na? Yn by capital D. So here, so in this case, if the d by lambda, if it is small values, then in this case, the tan theta approximately equal to sine theta. Tan theta approximately equal to sine theta. So that's why we'll take it as a sine theta only. Sine theta equal to what you tell me now from this now, yn by capital D. Okay. Yes, now we can place this one here. So this means delta x. From this we can write it as what? Tell me now. D sine theta. D into sine theta means what? You tell me now. Yn by capital D. This is the path difference delta x. Now here this is the path difference in this case, but practically, so here to have a bright fringe, so path difference must be how much now? N lambda should be now. Now I will equate it to the, to have a bright fringe, I will equate the path difference is n lambda. So this means delta x, and this we have equating to what? Tell me now here. D into yn by capital D, which is equal to n lambda. From this yn, which is equal to n lambda capital D by small d. This is yn. Yn equal to n lambda capital D by small d. Where n is, if I want the central bright, so central bright is also called a zeroth order bright. For the zeroth order bright, zeroth order bright fringe, or we can say this is central bright. Central bright. So in that case, n value 0. Then will come it as y naught, will come it as 0 now. Next, if I want here, if the similarly, if we have, so n value 1 we have taken, then we'll get the y1 will come how much now here? Lambda capital D by small d. And this is called as a first order bright. This is first order bright. And if n is equal to 2, then will come y2. That is what terminal 2 lambda capital D by small d. And this is called it as second order bright. Bright in the sense bright fringe. Like this we can get the, whichever the bright is required, the distance we can find. Okay. Now we'll find the fringe width. Fringe width.
Yes, sir.
Hmm. So like this, we have n value 1 means first order bright, n value 2 means second order bright. Like this, we can continue. Okay.
Yes, sir. Obviously.
Now like this, if we want the third order bright means n value 3, fourth order bright means n value 4, like this. Okay.
Okay, okay.
Now, so we'll talk about the fringe width. Fringe width. Fringe width means, okay, here we have the central bright is formed. Here we have a second first bright. So there is a gap between these two is there now. That gap is called as a
Yes,
fringe
sir.
width. Gap
Yes,
between the two successive first brights is called as a fringe width. Okay, the fringe width. That means what will be now here? The first order bright is here. Second order is like this. The difference between these two is called as a fringe width. Okay, so this means fringe width will denote as a beta, which will be given as simply y2 minus y1. Okay, so that means beta, which will be given as what will be now lambda capital D by small d. Now, if you do the difference between these two, lambda capital D by small d, right? This is the fringe width. Okay, here we have seen the bright. So here at the point P, dark also may be formed. So if at the point P dark is formed, that means case 2 if we call, if P be the nth order dark, then so how much will be the path difference to have a dark? Path difference delta x, which will be equal to how much now? 2n minus 1 into lambda by 2 to have a dark. And so this is, we have seen conditions, path difference is delta x, which we have seen. How the delta x we have seen? This is the d sine theta. And so that is nothing but, so d into sine theta, we got it as yn by capital D. Now we'll equate now here. So this is d into, this is yn by capital D, which will be equal to 2n minus 1 into lambda by 2. Then from this yn is equal to what, tell me now, 2n minus 1 into lambda capital D by small d. This is the distance of the dark fringe from the central bright. This is the distance. Okay. If I want the first order, n value 1. For the second order, n value 2. Like this, we can place now. So if I put n is equal to 1, n is equal to 1, then we'll get this y1 will come now. How much will come here? This is lambda capital D by small d. This is called as what? Tell me now here. First order dark. Next, if n value 2, then it will come to be what? Tell me now here. N value, if you put the 2, then will come it as what? Tell me now here. So here This is y2. Will come to be a 4 minus 1, 3, na? 3 lambda capital D by small d. This is called as what I'll now here? Second order dark. Okay. Like this, we can able to find out. Okay. Here onwards, we'll see some points now here. These points are very important. It's a summary. So any problem related to YDSE can be solved with this thing. Okay. So totally we can find the 20 points. You will find all the formulas. So these things are helpful. Take this thing one by one points. Distance of nth bride fringe from central maxima. Distance of nth bride from central maxima. So which will be given as, this is yn, that is given as n lambda capital D by small d. Next, distance of, for the dark I'm using m I'm using mth dark fringe from central maxima. So this is ym, which will be equal to 2m minus 1 into, I will write here, this is ym, which is equal to 2m minus 1 into lambda capital D by 2d. This is the distance of mth dark. Okay. Next, fringe width. Fringe width will called as a beta. Fringe width beta, which will be given as lambda capital D by small d. Fringe width. Fringe width of bright fringes is equal to fringe width of dark fringes. That means what will we know? Beta, the fringe width for the bright, which is also equal to fringe width for dark. Right. Next one. Fringe width fringe width is independent of order, is independent independent of order of fringe. Means what? Tell me now. The width is there now will be same whether it is a first, second, third, anything. The fringe width beta is same for all the cases. Where if it is a first fringe or second fringe, it doesn't matter. Okay. Next. Next. Fringe width depends depends on wavelength. Wavelength of light. Lambda is there now. That's why fringe width depends upon wavelength of light. And beta 1. Beta 1 is the fringe width. Beta 1 is the fringe width when YDSE means ends double slit experiment. When YDSE is in A and beta 2 is the fringe width. Beta 2 is the fringe width Beta 2 is the fringe width when YDSC is in some medium other than A. Then what happens? You tell me now here. So here, what is the basically fringe width is given as beta equal to lambda capital D by small d. So here wavelength, if you move to some other medium, what happened to lambda? Lambda will increase or decrease. What happened to lambda now here? Lambda if we move to some other medium, where the wavelength is more now, air is more or medium is more? Air only. That means beta 1 is the fringe within where you tell me now air. Beta 2 is the fringe within medium. So here the beta directly proportional to lambda. If the lambda is high means then beta also more. Right. So that means what we can say now where the fringe width is high now, air is more or medium is more. Where the wavelength is more. Where the wavelength is more. A. So that means beta proportional to wavelength only not directly proportional. So that means what I can say now here. So this lambda 1 will be greater than lambda 2 only na. Then obviously here what should be now beta 1 is greater than beta 2. Okay. So in A fringe width is more. Next and beta 1. Beta 1 is a fringe width. Beta 1 is a fringe width when a red light is used. Okay, and beta 2 is the fringe width. Now I'm using some other light now here. Let us say when blue light is used, then here you see this thing here. Which light will have more wavelength? So here we have VIB GYOR in this. If we move towards a red, what happened to wavelength now? Increase or decrease? Wavelength will increase. Now, which color will have more wavelength? You tell me now, red or blue? Yes, so this lambda of red is greater than lambda of blue now. So from this, what I can say now, beta red is greater than beta blue. Beta red means beta 1. So that is beta 1 greater than beta 2. Yes, fringe width is directly proportional to lambda. If the wavelength is more, fringe width is also more. Right. Next one. Yes. If YDSE conducted with white light, generally the light will contains all the colors. So the white light is a combination of all the colors now. White is a mixture of all the 7 colors. Right. Then what happens now here? If it is white light is done, then we have central bright is there now. Then central fringe is white. Central fringe is white, and the remaining fringes remaining fringes are colored ranging from violet to red. Okay, the YDSE, if you do with a white light, central is a white color, remaining fringes are colored form. Violet to red we can find. Next one. And if N1 number of fringes are formed, N1 number of fringes are formed when the wavelength of light is lambda 1. Next, N2 fringes are formed when the wavelength of light is lambda 2. N2 fringes are formed when the wavelength of light is lambda 2. In this case, then N1 lambda 1 equal to N2 lambda. N1 lambda 1 equal to N2 lambda 2. Okay? Distance. Distance between, we can write. Distance between nth bright nth bright and mth dark fringes. Hammer this distance is a which will be equal to mth bright. Nth bright is formed at n into beta minus mth dark is what, tell me now? 2m minus 1 into beta by 2. Okay. Next, maximum number of complete maximas. How many maximas are possible? So that is which is given as 2 into step of d by lambda plus 1. So step function you know na greatest integer function. Hmm. Next, maximum number of minimas. Complete minimas. How many are possible here? That is 2 into step of d by lambda. Why 2 means what will be na upar niche. Above is there, below also there. Same thing will happen. That's why 2 times. Next one. And highest order maxima. Highest order maximas. And that is given as step of d by lambda. Highest order minima. And which is equal to step of d by lambda plus 1 by 2. This is highest order minima. Next, angular fringe width. Angular fringe width will denote as the theta, which will be given as beta by capital D is called as the angular fringe width. Beta by capital D is the angular fringe width. Right. So we know the beta value. Beta equal to means what, lambda capital D by small d. So if I put the beta value here, then will come it as it. D will get cancelled now. It will come to be lambda by small d, other formula.
Yes.
Next one. Fringe visibility. Fringe visibility will denote as a V, and which is given as, this is I max minus I min by I max plus I min intensities. And we know the I max value. What is the I max value? Which is given as root of I1 plus root I2 whole square. I min value how much? that is root I1 minus root I2 whole square. Okay. Now, if I put this value, this thing I max minus I min by I max plus I min, if we simplify, then you can get the V value. It will come to be a 2 into square root of I1 I2 by I1 plus I2. This is of the form A minus B whole square. So we'll simplify now. A minus B whole square. We'll get it as fringe visibility as like this. Now, here the fringe visibility, it can be lies between 0 to 1. So 0 less than V less than 1 fringe visibility. Next, if I min equal to 0, then tell me what happens now. Minimum intensity 0. Here I min 0 if I place now here, then will come the V value will come it as I max by I max, then will come it as 1. Then that means fringes are clearly visible. That means fringes are very clear. In this case, we can say contrast is more. Contrast is maximum. Okay. In some cases, so here if it is a I min equal to I max, both are equal. In this case, this value V value 0 means visibility. That means you cannot able to distinguish the bright and dark. Both will appear same only na. In that case, the fringes are not visible. No fringes in this case. So, and this is called as a uniform illumination. Uniform illumination. No fringes, uniform illumination. Right. These are the formulas you need to remember for this YDSE. Okay. And for the interference, also I'll summarize the formulas. You will take that one, these formulas also, interference also. And we are continuing these formulas. 5 more formulas will come. This is interference के लिए. Interference के लिए what formulas you need to remember here? Resultant intensity formula. The resultant intensity, tell me now, which is equal to A1 square plus A2 square plus 2A1 A2 into cos theta. This is a resultant amplitude, and the resultant intensity is what, tell me now? That is I1 plus I2 plus 2 root of I1 I2 into cos theta. Okay. This is the resultant amplitude and the resultant intensity. Next. And for constructive interference, the condition is what, tell me now? Constructive interference. How much the path difference? Path difference delta x, which is equal to n lambda. Phase difference is how much? 2n pi. In this case, we have a maximum intensity. That is maximum intensity is A1 plus A2. maximum amplitude, maximum intensity. Intensity maximum is how much now? That is root I1 plus root I2 ka whole square. This is for constructive interference. Right. Next. And for destructive interference, the conditions are what? Tell me now here. Path difference is how much? 2n minus 1 into lambda by 2. And phase difference is how much? 2n minus 1 into pi. Okay. And in this case, we have a minimum intensity now. How much the minimum intensity, which is equal to A1 minus A2. Minimum amplitude. Minimum intensity is what? Tell me now, root of I1 minus root I2 whole square. Minimum intensity. Next. So what is the ratio between Imax, maximum intensity, by minimum intensity? Maximum intensity by minimum intensity, which is equal to what? You tell me now. So this is, which is equal to, that is root of I1 plus root I2, and this is root of I1 minus root I2 the whole square. And that is also equal to what we can say now, A max by A min. A max by A min whole square. Intensity proportional to square of the amplitude. And intensity proportional to square of the amplitude, that is proportional to directly the width of the slit. W is width of the slit. We can write this as I1 by I2, which is equal to A1 by A2 whole square, that is also equal to W1 by W2. Okay. Next one. Next one is missing wavelengths. Missing wavelengths. Missing wavelengths means the wavelengths which are not appears. So for the missing wavelengths, we should have a destructive interference has to happen. For missing wavelength, the condition is what? Tell me now. For missing wavelength, destructive interference will occur. destructive interference. Now let us consider we have taken here we have taken the two slits, and here this is the screen we have taken. Now so here this is the source. Now here we have slit S1, here we have slit is S2. The light ray which will come here go, and here one light ray will going like this. Now we need to find the missing wavelength exactly in front of the slit. We need to find this light ray directly will go here, exactly this point we are finding, and this is the light ray, this much distance this light ray has to travel. Okay,
Okay.
now look at now this point we are calling it as a P. This is the screen, right? So we have taken so this point. Now this is, we'll see this time the distance from here to screen to the slits. This is the capital D. Now you tell me now here, how much the S1P distance you tell me now? S1 to P distance is how much? Here to here the distance, now that is a capital D. Yes, now here, now the distance between these two slits is there now. This is how much now here, small d, right? So that means now, so look at now here, this is capital D, this is small d. Now this is the hypotenuse only now. So that means how much the S2P distance? Yes, S2P, that is a hypotenuse now, square root of what, tell me now? D square plus small d square. Yes. Now here this is the, now we need to get the path difference now. Path difference delta x, which will be equal to what, tell me now? S2P minus S1P. Now, so this delta x, which will be given as S2P, which is equal to square root of d square plus small d square minus capital D. We are doing some binomial approximation we are doing here. Now, if I take as a capital D common outside here, then will come it as capital D outside, then it will come to be 1 plus small d square by capital D square, this power 1 by 2 minus capital D. Yes or no? So basically, so this capital D is which is very much greater than small d. Right, so that's why if you take this thing, 1 is very much greater than d by capital D, na? So that means d by capital D, which must be very much less than 1. D by capital D is very small. So we do the binomial approximation. That is what, tell me now? We have 1 plus x whole power n. If x is very small, we can approximate this as what, tell me now? 1 plus nx we can say now. So from this, what we can write, you tell me now, delta x, which will be equal to capital D into what, tell me now, 1 plus, the n will come it as a coefficient, that is 1 by 2 into what I will get, you tell me now, d square by capital D square minus capital D is there now. This power 1 by 2 will come it as a coefficient. Now, so how much will get this my path difference now, delta x? which will be equal to capital D into, tell me now here, this is 1 plus, this we have, what, tell me now, D square by 2 into capital D square minus capital D. If we multiply this thing here, what will come here? D plus, this is D square by 2D minus D. D will get cancelled. How much will get the delta x now here? D square by 2D will come. Check this thing. This is my path difference. Okay.
Okay.
Now, so here what we need to do here, we need to find out the missing wavelength. For missing wavelength, what type of interference has to happen? For missing wavelength, it should be a destructive interference. Okay.
Yes.
So here that means for destructive interference, what is the path difference, you tell me now? For destructive interference, and what is the path difference condition? So that is delta x, which will be equal to how much now? 2n minus 1 by 2. So we should equate now here. So that is 2n minus 1 into lambda by 2. That is equated to what term? D square by 2d. So then from this 2 will get cancelled. So lambda will come to be a what term? D square by 2n minus 1 into capital D. Okay. So this is, so if I put n value 1, so what happens now? So from this we can find the missing wavelengths. Tell me now here, n value 1, missing wavelengths. If I say n value 1, so tell me now, how much will get the lambda value? Tell me now, n value 1 will d square by capital D na? Yes, n value 1, 2 minus 1, n value 2. Yes, so will come to be 3D. Next what will come? N value 2, 5D. Like this will come. Okay. These are the missing wavelengths. Okay.
Okay.
Hmm.